So I'll go ahead and get started. I am Jeremy Martin. I work for Unity in the multiplayer group. I'm responsible for most of the technical components of the service backend that facilitates network play over the internet. So in this talk, I want to talk a little bit about how our service comes together, the things that go into it on the inside, and put together like a picture for you on how we work. So for the service itself, this overview kind of has a very generalized flow on how traffic comes into our system and is handled once it's there. The block arrows at the top are external traffic to and from the internet, and it starts up here at the top left. So we have generally JSON REST requests that come in through the load balancer that are handed off to the Matchmaker. The Matchmaker is just a normal web service. And you can also, even though there's like a single block diagram for this, each of these individual components in our backend is clustered for scalability and for fault tolerance. So the load balancer finds a matchmaker to hand the request off to. The matchmaker interacts with our database layers and our memcached backend, and then communicates with Relay via the message queue system, and I'll talk more about that in a minute. And then the individual Relay servers have matches that are created on them, where people have seats assigned and IDs set up, and their security is basically verified with our backend system against the game config that they have in the account service. And then Relay is ready to handle the UDP traffic, which is the block diagram at the top right, which is just the normal UNet networking protocol. So right now, the timing is kind of perfect for this talk because we're doing a pretty big refactor and partial rewrite of some of the components for the multiplayer service. It's been live for a couple years, and it's been growing. We're very happy with it. It's currently good, but we wanted to go back and make sure it was future-proof with regards to where it's going in the future, as well as adding features and trying to improve overall performance on our backend. So one problem that we've had on our backend is occasionally, and super occasionally, messages can fail to deliver between Matchmaker to Relay. And those tend to be commands like creating matches or cleaning up users or things like that. We'd really only see it in land rush scenarios. So when we have like sudden spikes in traffic, a game goes live, something like that. Like some small percentage of our requests would end up failing because our message queue system was overstressed. So we wanted to go back in and kind of fix that, make sure that that couldn't really happen. Also, the previous architecture for the multiplayer backend service for the message queue required that we always interacted with the database to do a lookup for the service on the backend on specifically, say, Matchmaker, what Relay server does it need to find to talk to, and then connect directly with that socket. And that can be really cumbersome. And also databases, they just don't scale as well as like some other systems you can use to do the same trick. So we replaced the message queue. Previously we were using 0MQ, and overall it was really good, but it wasn't as full-featured as we ended up needing as we started to add more servers and grow the service internally. So we're switching off with the new server version that's going live very soon to RabbitMQ. It supports guaranteed message delivery with optional persistence. And because of that, we've been able to completely hack and slash out large sections of our database layer. We don't need to address servers. On the back end, all traffic goes through channels, RabbitMQ channels, which is really handy for us. So instead of needing to know a specific Relay server is hosting a match for a specific game, Matchmaker, when it gets a request related to that match, or that game, it can just send messages off through the RabbitMQ server to, like, it's a text string basically, and RabbitMQ resolves where that needs to go based on who's subscribing to those channels. RabbitMQ is also really good in that it provides load balancing for us. It'll automatically round robin to Relay servers, so it helps spread the load between Relay server 1, 2, 3, 4, 5, and then it'll start back over at 1, 2, 3, 4, 5 for create match requests and things like that. And of course, we get clustering and fault tolerance, which is something that we didn't really have for free in 0MQ because it's more an embedded message queue that was its job is more to facilitate message and socket delivery. I should also mention the entirety of these messages going through our backend system uses Google protocol buffers in a binary format, which is a very small, very efficient encoding library for us to be able to keep the message size small, which is important to keep like memory footprint small in the message queue overall. So yeah, from switching over to RabbitMQ, we were able to learn a lot of things. No technical solution you go from and to is going to be completely problem-free when you're dealing with complex systems. And the first thing is guaranteed messages are not necessarily quick, they're guaranteed. So you can be confident that they're going to get there. You may have issues if you expect them to get there in under like a couple millisecond window or something like that. Likewise, in message queue systems in general, this isn't a knock on RabbitMQ or ActiveMQ or Microsoft MQ or any other message queue system. Generally, when you enable persistence on a message, which means that message will be checkpointed to a disk or a database in case of a crash on the message queue server. When you enable that feature, like just the disk access is going to slow down the system a lot. So you really want to be careful about when you're dealing with a back-end message queue, whether or not you enable persistence for each of your individual messages and kind of custom tailor the flow for that. In our system, we ended up needing persistent messages, I think for maybe 1 or 2 out of like the 20 message types that we end up sending through the system currently. Also, so this is kind of an interesting one. If messages logjam, look for message pump stalls in your code, and by that I mean when you're dealing with a message queue, you generally have a client that's connecting to a message queue server, and it's just waiting for messages in its threaded loop. But you can actually introduce problems where it looks like the message queue system isn't delivering messages, but that's simply because all the message pumps on all the servers that are available are busy doing other things. One thing we ran into specifically when we were switching over was there's this series of messages that would send a message from Matchmaker to Relay, and then actually from Relay back to Matchmaker, because Relay doesn't talk directly to databases. And in order to have the transactional integrity, it needed to do that hop. Matchmaker would then reach out to the database. But then if we had something that made that database transaction start to log jam or go slower, that would completely make the other message queues kind of stall for a bit until that final one completes, because everyone else is waiting for that one transaction. So you want to kind of have an idea of like what tasks you can make asynchronous in that system, what actually needs to happen before you can complete and notify everyone of success or failure. And likewise, kind of related but not identical, is plan multi-threading use when you're dealing with message queuing systems on the back end. It's generally very easy to have a message pump that's going to receive messages on one thread, but sometimes that's not enough, particularly when you're dealing with cloud servers that have a lot of CPUs. You really want to try and take advantage of that. So always have an eye towards like, when you're dealing with RabbitMQ, when you're dealing with ActiveMQ or something like that, like what's their best use to actually multi-thread that and preferably have multiple message pumps going for delivery at the same time. So another problem we kind of have been running into for the last couple of years is a code reuse problem, which is a fundamental issue in most software design. Our backend is primarily C# and C++. Relay is a C++ server, and Matchmaker is a C# web stack. But the issue is when we needed to have both servers use a similar feature set or talk to something on our back end that was a shared feature, say a message queue feature or our logging or database or something like that, it would take twice as long to write because we have to write it once in C# and another time in C++. It leads to maintainability issues. It's harder to test. Frequently, we run into issues where the library that was coded for C# would have a feature that was not yet implemented in C++ or vice versa. And we started to get like asymmetric code paths based on that. And it was becoming a total mess. So just going forward, to simplify that, we made the decision to eliminate most native code unless it's really needed. Previously, Relay server was a C++ Windows service executable. And that's been migrated over to be a DLL that's now loaded in a managed container. The managed container is a C# exe service that just loads up the DLL, but it also handles the core functionality of message queuing and all the various tasks that go into the inputs for the DLL. And then likewise, Relay Server has the ability to call back out from the managed code. I should say, like, Microsoft makes it very easy to go from managed to native, and very difficult to go from native to managed, but it is completely possible to call C# assemblies from C++, like not managed C++, like normal native C++ code. And yeah, I kind of mentioned here, like the reason Relay Server really has to be native is because it's built on top of I/O completion ports in Windows, which is a very efficient way of handling socket delivery in a multi-threaded manner. And I'll get into some of the numbers related to that and why we've made that decision and kind of stuck with that over the years. So yeah, we were able to delete our native logging, server-to-server message systems, database interfaces. Almost everything went away for shared auxiliary code, like non-core path code for Relay Server. But most notably, we did keep performance counters native because there is a performance penalty going native to managed on that function call, and you really want to be aware of that if you have something that could be called, say, in a tight inner loop. So yeah, at a minimum, from what we've seen, like going from native to managed, like you're looking at least a 10% hit on a function call, and that's probably a relatively trivial function call. That can get worse if you're passing a lot of data and you have to marshal stuff between the native and the COM to the managed heap, or vice versa. There's a lot of mem copies in there. So always have an eye towards that, and the biggest trick that we really relied on this transition was to just early out stuff in like native code whenever we could. The example I have here is logging levels. We, instead of always passing a log line off to the native code, we look at the log level and we determine, is this even going to be written out anywhere? If it's not, we don't even bother calling and doing that marshalling and that transition for that string and everything else. And that allows performance to be still really good in our system, even though we kind of have this like transition layer for code reusability and easy use and testing and whatnot. So I wanted to talk about some new features that we've been working on our back end too. This isn't necessarily facing to our users, but it's going to improve our quality and our consistency as we go live with new server versions. And that's a new stress testing framework that we've been working on to allow us to automatically verify what kind of load our servers can handle. The stress testing framework itself is actually just a normal Unity multiplayer game project that's been made, and we run it in batch mode, no graphics, strip out everything we can, and we have the main loop run at 10 hertz, sending an aggregate of 4K per second, which is about, it's at a default, and it's where we expect a lot of games to be, and based on what we've seen for our metrics, that's in line with what most of our developers are doing. So each of these Unity multiplayer clients will then be loaded onto a cloud instance, and we keep executing it while there's available CPU time on the cloud instance. And we've noticed on larger instances with a lot of CPUs, we can easily get up to like 500 or more, as many as 700 clients per physical machine, per VM. And then we just spin up a lot of VMs. And we use that to try and establish exactly what the limits are for our system, how it behaves at the hairy edge, and you know, if there are actually problems we need to address. I mean, at some point, you're going to be dealing with a system that's so overloaded, there's nothing you can really do about it. The solution is to add more hardware. You want to make sure that you gracefully fail and that you have enough overhead at the end of the day to accommodate any kind of sudden growth you may have in your system and allow you to, like, you know, have auto-scaling work or throw more machines at it or whatever's necessary to do once you get those ops alerts that come in the middle of the night. So that leads us to the line down here I'm pretty happy with. For a single matchmaker and relay pair, our CCU count, which is concurrent users in our system, is going to be around 30,000 per physical machine. And that's running on a relatively modest instance with, I think, it's mostly gated by our relay server because it's doing the actual packet relay. But I want to say that only has 2 physical CPUs, 4 with hyperthreading. And it's able to keep up completely fine on that. And we never really want to run our servers that high. In fact, our target per relay server is only 5,000. And the reason we do that is because we never want to have so much of the service running on an individual machine. If we have an issue with, obviously crash issues can happen, VM issues can happen, there could be a problem with the network router, where the machine's located. You can have all kinds of things that'll take out an individual machine, and we never want to be in a position where we take out 30,000. We'd rather be taking out 5,000. So really what this means is, with the stress testing we've done, we've established that Relay runs at roughly 15% CPU usage at the expected target that we're trying to hit. And the last part's really important. This is part of our deployment process going forward. So we're going to be looking at every version, regressing it, make sure that we don't have any new unexpected performance problems. Hopefully we'll just be doing an uptick on performance every release that we do. This is developer-facing, so you guys will be able to see this in the near future after the new server version goes live. We're going to have a graph panel, and I sadly couldn't get a graphic together for it in time, but it's a graph panel that's going to show you how your game's behaving in the Unity multiplayer service. So you're going to be able to see a lot of stats on a 1-minute resolution for when players join, when players leave, individual matches that are running, your total CCU count, the bandwidth used per match, the bandwidth still available for that match at that point in time. Just a lot of things are going to go in, so you're going to have a better idea, live and historically, of exactly how your game's behaving. So this is another new feature that's been highly requested for us. We're adding NAT punch-through to the multiplayer service. So for a brief introduction, NAT is network address translation. It's required because IPv4 has an address issue. There just aren't enough of them. Everyone in this room probably knows that IPv6 is the future, and IPv4 is kind of an out-of-room protocol that we've been trying to manage and massage for years now. And NAT is the biggest strategy that everyone's doing. So almost every home router that's hooked up will automatically establish an internal IP range that you've probably seen, like 192.168. That is an address that you'll never find on the actual internet, which means when a packet is sent out on your local network, the router's going to know that it needs to look inside in order to relay that packet and find out who's delivered to and whatnot. And if it's not that, then it hands it upstream to the intranet. NAT actually works when it does hand something up to the upstream router. It keeps track of who it's talking to internally, so it has a mapping of this internal computer, smartphone, whatever, wants to go talk to this server. This server, I'm going to relay that request up to the server. When the server gets back to me, I'm then going to repair that packet and forward it along to the computer in question. There are 4 different NAT types, and I won't go into the differences for each of them right now, but there's full clone, address restricted, port restricted, and symmetric NAT, and that just kind of says the kind of complexity that you deal with in NAT configurations. So NAT punch-through is what you do as an optional feature, or at least that's our plan, to fool the router you have at home or the router you have at work or something like that, into, instead of talking to that upstream server, so Google.com or CNN.com or something like that, it allows you to send packets between 2 home routers, as if those machines are on the internet as hosts. If you don't use NAT punch-through, your options are pretty limited to get a computer on your home network onto the internet, and that usually involves port forwarding. UPnP is kind of being phased out, but that's basically what that accomplished too. But NAT punch-through is there as a kind of clever way to do that automatically, where the user doesn't have to do any special configuration in their router, which is the most important part for us. So yeah, the strategy that we're using with this is specifically Relay is there because Relay is a 100% available service that speaks our protocol. It's always there. Computers can always connect to it. But we're going to allow developers to do NAT punch-through first to try and see if they can establish a connection directly with the other clients in the match. And if that's possible, then no traffic would even go through Relay service. So in order to accomplish this, we're running a facilitator on our backend with a good authentication mechanism. And we rely on NAT punch-through is hole punching, basically. And there's a diagram here that I have. So starting from the top, the host number 1 connects to the facilitator. The client number 2 also connects to the facilitator. They register. They have their GUID set up. And then they go through this handshake where the client and the host end up talking through the facilitator to get the information they need to change their packets to make it look like data is kind of coming from the facilitator. So that means when that packet is sent out from your home network, it'll be routed directly to the other person's home network. But the packet header is set up in a way that it kind of looks like it's coming from the facilitator, and that will allow the other person's home router or corporate network or whatever to be able to understand and do the NAT repair automatically and then forward that packet along to the correct internal client. As you can probably guess, this is non-standard, which is why reliability is an issue and why Relay is still there and still the 100% available solution as really a backup. In our testing and our research, we find that NAT punch-through, depending on where you are in the world and what sort of internet topologies you're looking at, and specifically if you're looking at a home router or if you're looking at a corporate router, something more professional, the reliability of NAT punch-through can be anywhere from 30% to 90%. It's rarely going to be 100%, specifically because higher-end routers are going to be looking for this exact type of thing going on, and a lot of them will try and stop it. So when that happens, Relay is going to be available to facilitate the traffic in the match in a mixed mode so that some clients can connect directly through NAT punch-through, some clients will connect through Relay. For this last part, I just wanted to throw out a couple things that are common user issues that we run into that I just want to make sure everyone's aware of. We get this question all the time, the difference between drop connection and destroy match on the matchmaker. Destroy match is not there. It's an emergency cleanup function if you really need to make sure a match is ended immediately. The normal flow is for when a match is stopped on the client, it'll automatically call drop connection on all the connections. And when all the clients have done that, then the match is ended automatically. So there's no reason in a normal flow to go out of your way to call destroy match unless you specifically need to emergency stop a match. The names that are handled for matches, which is a string field that you send up in the create match request, those are wildcard matches, so that can actually be kind of powerful when you want to enumerate other matches. You can play some games to match against star, wildcard star, if you're looking for specific match features or something like that. Always use the page feature of list match. Generally, you'll return a certain number of results, but there could be many more on a subsequent return. So start at the first page and then work your way up on there while you're looking for matches on the list match request. And it's also worth noting that ordering coming back from Matchmaker on a list match request is purposeful. It actually orders according to geographic location. So Matchmaker will return the set of matches that are closest to you in the world first, and then order out from there. The one exception to that is if you use the ELO score when you're creating a match, that is, you try and say what the current skill is for that user, you end up with a match ordering that's ordered by ELO set, and then inside identical ELO score differences, then everything's ordered geographically. And also, this one's really important. In our service, you have the option to go live. So by default, you have a 4K per second limit at a certain number of CCUs, depending on what license you have. Definitely, if you have a game that's going live, turn on the Go Live feature in the multiplayer configuration. You won't be charged anything just by doing that alone. You're only charged for bandwidth that you use in the system. So that bandwidth limit is there for you to be able to say, kind of draw a line in the sand. I don't want to go over this when using the multiplayer service. I don't want to be charged for more bandwidth than this. But it's a ceiling, and you get to manage that directly. So yeah, thank you very much.